Consider the fusion reaction shown below. A proton fuses with a deuterium nucleus, which is a hydrogen nucleus with only one neutron. Sorry, not only one, just one. They often don't have a neutron. In the sun, a helium nuclide is formed and a gamma ray released. 20 mega electron volts of energy is released during this process. Now, have we heard of electron volts before? No? Okay. Electron volts, I'll show you the conversion factors shortly. Electron volts are a measure of energy. Okay, you can convert them to joules. And in fact, part B asks you to do that. So I'll show you how to do that shortly. Okay. So part A, what is the value of the unknown mass number x? So like I said before, you just have to add your numbers up going across. So we have on the left a 1 and a 1, so we have a 2 for our proton number. Okay, our mass number, we have a 1 and a 2, which must be 3. Yep, so the unknown mass number is 3.
Did we ever get a question like that?
Oh yeah.
Yes, really?
Oh yeah.
Yes.
How much energy is released in joules? Now we are going to look at electron volts in a lot more detail later on this year. But for now, the conversion factor is 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. Electron volts are tiny. Okay, electron volts, funnily enough, the name makes perfect sense. It is the amount of energy a single electron gets going through a single volt of potential difference. That is an electron volt. So it is a very, very small number. So we had 20 mega electron volts. What does mega mean? Capital M, what does it mean? Times 10 to the 6. Mega is times 10 to the 6, so it's 20 million electron volts. So to find out the number of joules, we just take 20 times 10 to the 6 and multiply it by the conversion factor. Just like that. If someone wants to help me out with a working calculator, that'd be great. 3.2 times 10 to the negative 12. Thank you very much. And that's in joules. So we've converted our electron volts to joules. Okay, finally, calculate the mass defect for this reaction. All right, that's Einstein's equation. E equals mc squared. Our mass defect, well, we could actually write this. Hang on, let's write this properly. Our change in energy is equal to our change in mass times c squared. So we want our change in mass. That's our mass defect. Okay? So if we rearrange our equation, our change in mass is equal to our change in energy divided by c squared. You should already be able to tell this is going to be a very, very small number. So our change in energy is the amount of energy released, 3.2 times 10 to the negative 12, over our speed of light. I worked this out earlier. What did I get? No, that's not it. No, can't find it. Anyone got it? 1.06? Times what? 10 to the power of 20? Yeah, I think that seems very large. Negative 20? Right. Yeah, what did you get? 3.56 times 10, negative 29. That sounds better to me. If you didn't get that, make sure you're squaring your speed of light underneath. I reckon that's where you might have gone wrong. Yeah, I reckon that sounds better to me. Okay, and that is mass, so it's in kilograms. So in this reaction, we are only losing 3.56 times 10 to the power of negative 29 kilograms, which is a very, very small amount of mass. Okay, but Well, I guess it's a very small amount of energy as well.